All right, so in the previous video, I talked about an LC circuit, which is just an inductor and a capacitor, starting with some amount of charge in the capacitor. And in that case, the charge and current will effectively oscillate back and forth, right? Current flowing clockwise and then counterclockwise, and the energy moving or changing completely from electrical to magnetic and back and forth, right? This takes some time, and so there's some frequency of this oscillation, which we'll determine at the end of this video, okay? So the previous one was more of a qualitative overview. This one will be more of a quantitative overview, right? We'll see what the actual mathematics are behind these LC oscillations, okay? So the total energy in an LC circuit is, well, the energy of the electrical, right? Or basically the energy in the capacitor plus the energy from the inductor, which is the magnetic energy. And these have the forms of Q squared over 2C for electrical, and then Li squared over 2 for the magnetic. Okay? And because these are just an inductor and capacitor, it's not connected to another voltage source or a resistor, it's just an LC, that means that this energy will remain constant, right? The current will flow back and forth, reverse directions continuously. So because of that, we should be able to write dE dt equals 0. So let's see how that changes our equation above. So that means that we're taking the time derivative of the first term, q squared over 2c, and plus the time derivative of Li squared, over 2, right? Both of these terms are functions of time, right? Q is a function of time, and the current I is a function of Q, and thus a function of time as well, okay? So keep the picture in your mind from the previous video, right, of this LC oscillation and the current going back and forth. So let's see. If we take the time derivative of the first term, we get Q over C. And if we take the time derivative of the second term, we get L times di dt, right? And we can write this, or both terms, as functions of Q. I'm going to squeeze this in here, plus L, and then di dt is just d squared Q dt. It's the second derivative of the charge, okay? And so again, this equals 0. Okay. You may recognize this from 4a, right? It's okay if you don't. I know it was a while ago, but it's similar to the situation of a mass on a spring, right? It's similar to a mass spring system, which was basically you have some spring with some spring constant attached to a mass on a frictionless track, right? Mass m, spring a constant k, and this can move back and forth, right? And if that's frictionless, no energy is lost. We're assuming the spring doesn't heat up due to friction, and this is in a vacuum, right? If that mass is pulled out to some maximum displacement and then released, that will oscillate forever, okay? And so that had the form, the energy in that had the form of 1/2 mv squared, kinetic, plus 1/2 kx squared for the potential, right? The spring potential. And so that had a solution like such, for position rather, right? Solving that as a function of the position, because v and x are both functions of position and time, we get, well, the initial position times cosine of some stuff, right? Remember this omega right there, omega, that was the angular frequency T is time, and phi here is some phase constant that's determinable based upon boundary conditions, right? I don't want to go too far into that yet. But this is the form of the solution to the energy equation right there. So now going back to an LC oscillator, we have a very similar form right there. But instead of being a function of x, it's a function of q. So now for an LC circuit, our solution is the following. Let me do it capital. Q as a function of time is some initial charge times cosine of omega t plus some phase constant that can be determined based upon other stuff, right? For right now, just it's cosine of stuff, okay? So if that's our solution to this equation, right, and thus our solution to this equation, what the heck is omega, right? That's the key to this video. We have to find omega. And so let's find the current as a function of time, which is dq dt, right? That means it is negative q naught times omega times sine of that stuff, right? And actually, we'll need the next derivative. We'll need d squared as well. Yeah, we can do that there. D squared q dt squared, right? Because what we want to do is plug in q right there and plug in d squared q dt squared right there. Set it equal to 0 and see what omega is. Okay, so let's see. What is this? Take the next time derivative. We have minus q naught. Now we have omega squared. Derivative of sine is cosine. Argument stays the same. Okay, so now let's plug in q and the second derivative and see what we get. I hope I have enough room. So we're plugging it into q over c. So in other words, this, right? This was our q of t, and I plugged it in for q right there. Now we need to find or plug in d squared q dt, which we found right here. So now I'm adding, or actually I'm subtracting L times negative q naught omega squared cosine. Okay, and that's all equaling 0. So thus our cosine cancels out, right? And let's do a little bit rearranging. We have a negative in the second term. So what we really have is q naught c equals L q naught omega squared, right? So our q naught cancels, and solving for omega gives us a square root, or a 1 over square root of LC, right? And this is the angular frequency for an LC circuit, right? This is the solution. This is the form for omega in an LC circuit. So remembering back to the previous video with that giant diagram, those eight pictures, the omega here is the frequency at which the current flips direction, okay, to complete one complete oscillation. So from picture A, going around to picture E and back around to picture A, this omega, this expression, is that frequency, right? And remember, it's an angular frequency, so units are in radians per second, okay? And to kind of put this into perspective a little bit, like, let's say we increased or have a really high capacitance, right? If we increase the capacitance in an LC circuit, how does that affect omega? Well, if you increase C because it's on the bottom, it would decrease omega, right? You would have a smaller frequency. And thinking about that, if you had a larger capacitance, that means you would have a larger voltage with which to push charges around that circuit. Okay? So it would take less time. If you had a larger inductance, a larger value of L, that means that the magnetic flux would be larger, right, and would create a larger induced magnetic field, right, and so would also contribute to pushing the current around the circuit faster. Okay, so this is the angular frequency with which the current or charge oscillates in an LC circuit. We did that by saying that the total energy in the circuit is constant. It does not change. So that's the energy, and it does not change because we set the derivative with respect to time to 0, right? Took that to its conclusion, right? And we found Q, dQ, d squared Q, and plugged in the terms that we needed to and solved for omega to get this expression. Okay, so thanks for watching. In the next couple videos, we'll be using this omega to solve other problems, and well, I hope you enjoy. Thanks for watching.